Um, I think all of you have given me information about your project, team stuff, so that's good. For your proposal, all I want is a short document, no more than 1 page, one per team. Both members in the team don't have to submit it, and you can do it through Canvas. The submission window is open right now, and all you have to do is tell me 2 things. One, what will you be working on? What's your project? And don't just write 3 words. Maybe write 3 sentences. And the second one is, why is it interesting? Why is it interesting to you? Why should it be interesting to me? Why is it machine learning? And how do you plan to use machine learning? Why is it relevant to the class? And spend some time thinking about it. It doesn't have to be really complicated. Just make it as simple as it needs to be. Any questions about your project? Yes.
Do I have to say what kind of the algorithms we use?
You could give any and as much information as you want. For example, let me a hypothetical example. Suppose you want to, let's say your project is, you want to build a classifier that can identify what is the species of some tree based on a photograph. You can do things like, I found this great data set about trees. It's interesting because it's clearly a difficult problem because a program can't do it easily. And we will explore various feature settings and maybe a couple of algorithms. We'll explore how to make this work using, say, Perceptron, support vector machines. It does not have to be extremely detailed. One thing that I do want to point out, a couple of people asked me, and I just want to make it very clear, when you are picking your project, try to make sure that you don't spend your entire semester collecting data, because this is a machine learning class, not a data collection class. So make sure that you don't, you have a very clear plan as to where if your project involves an application, you have a clear plan as to where the data is going to come from. Yes.
Right now, my partner and I were petitioning third party for the data to try and work together for ours. I was just wondering, if they end up declining, is there possible to provide us data? Could we possibly make an amendment or?
Sure. Yeah.
Thank you.
The point of this proposal is I'll read them and get back to you and say, this is completely not feasible, or this looks like it's too simple, or it's perfect, carry on. And that's really, I want to start this process early. It's not like an exam or it's not a contract where you have to, given this thing, I'm going to, in December I'll read your proposal and it's like, aha, this person said that they're going to do this, and they, voided the contract somehow. It's not that. The point is to get the conversation going. Yes?
If you're working on some application on machine learning, do you have to remove the algorithms?
I would prefer that if you can, unless it's something that you absolutely cannot do.
And if we need some external library for that, should we make sure that it will run on CAD?
No, not really. You'll be running your project, and the deliverables will be completely in the form of written content, just like papers. Think of it as a tiny little paper submission sort of a thing, where at the end of a semester you'll be writing a small report about 6 to 8 pages long that will tell me everything I need to know. Yes?
So I read on the syllabus, you definitely don't want us double dipping on this from like projects from other classes. If we're doing a different project that has a component that could be applied in a different application, could we do that?
So in your project proposal, make it very clear what the differences are.
So there's just like an overlapping concept. And it's
Right. Make that very clear, and also mention what is the other class. If you want to double dip with your own research, I'm all for it.
Okay.
Other questions about projects? Some of you have already started discussions on the message board about this. I encourage you to start early.
So,
Yes.
A quick question on the homework. Epochs, just when you say run it for 10 epochs, that means shuffle the data, go through it.
Yes, we'll get
entirely 10 times.
Yes,
Thank
and I'll be talking about this, the batch variant of Perceptron at the end of today's lecture. And if I'm guessing right, at the end of maybe today's lecture or by the beginning of the next lecture, everything in homework 2 should be doable. Okay? If I time this correctly. So we are talking about online algorithms. Just to remind you, the game that we are playing is we are talking about learning algorithms that proceeds in this sort of rounds, where every round the learner is an example and it makes a prediction, and if the prediction is incorrect, it corrects its own hypothesis. In the last class we saw a proof of concept that online algorithms are possible, or mistake bound algorithms are possible, using this algorithm called the halving algorithm. And then we got started with probably one of the more famous machine learning algorithms out there called the Perceptron. And we'll continue on this right now. Any questions about last week's lectures? Right, so let's start with Perceptron. Just to remind you, this is an old algorithm. It was invented in 1958, and it is an online algorithm, meaning it processes one example at a time, and there are many variants. We'll come to the variants at the end. And the algorithm is rather simple. In the last lecture I went through this. I'm going to start at this point again.
I'm sorry, I have a question on the halving.
Yes?
So you say the end condition is that we leave only one. There are
For that in the homework. In practice, what happens is, or not in practice, what might happen is you will never, let's say all the functions in your hypothesis class agree, and they always agree. That means you will never end, right?
Yeah.
Does this mean you made a mistake? Is this a problem? Not really, because you will not make any more mistakes. So the official end is when you stop making mistakes. And if you've got only one function that is always correct, and only one function, eventually you will come to a data point where the rest of them will make mistakes, right?
Yeah. So you mean we will end after several predictions that are all right?
There is no end. I mean, the algorithm keeps going on forever.
Forever
Until one of two things happen. Once you hit infinity, time stops. Or you have only one function and you know that there's only one function that's consistent, which means you're done.
Oh, so that's why you tell us not to implement this one, because it might
Yes,
go
exactly.
infinite.
Exactly. Especially if you have function hypothesis spaces which are infinite. So you're not going to ever end,
Okay.
right? So let's start with the Perceptron algorithm again. The input to this is a sequence of examples, and just to remind you of the convention we've been following, x's are examples and y's are labels. And the examples are n-dimensional vectors. So we are given a sequence of n-dimensional data points, and what the algorithm does is, again, it's an online algorithm. So a new example comes in, the classifier makes a prediction. Remember that the Perceptron algorithm learns a linear classifier. So the classifier makes a prediction like all linear classifiers, which is it has a weight vector w, and it takes the dot product of this example that comes in and looks at the sign of the dot product. If it's greater than 0, it says true. If it's less than 0, it says false. Either way, you have a prediction, and then you compare the prediction with the true label. And if there's a mistake, then you update. And the update rule is in blue on the slide, and it's fairly simple. the new weight vector, Wt plus 1, is the old weight vector, Wt, plus some learning rate R times the product of the label and the example, R times Yx. And you carry on. So we saw this at the end of the last lecture, and I made this point about the bias, and I'll keep making this multiple times because this is one of those things that all of us forget at some point. So just remember that it's important to have a bias term in your weight vector. So the true prediction should look like W transpose X plus some scalar B, but we can always fold B into the weight vector, make it the 0th weight if you want, by adding the 0th feature, which is always a constant. And that's the setting that you guys are exploring in your homework, where the experiment section, you will not have a bias, you don't have to use a bias term in your implementation, because if you look at the data, the first feature in every example is the constant 1, always. So I have kind of made it simpler for you by doing that. A couple of other minor points. Yes, yes, question.
Okay, so if it's rolled up into the data and we do the dot product with our weights, that means the bias will always be 1 because we're not going to add it.
No, you will. You added, so the bias will not always be 1 because, so, right, so let's think of it this way.
Well, the weight should be 0 to
So let's say you have two-dimensional examples,
okay.
which means I have 3 numbers to learn. The W0, let's call this B, the first W1 and W2. So your X example, let's say, looks like a bias feature and some X and X1 and X2. And let's say I add this, I automatically add the constant term. So, does that answer your question?
You add the first.
So let's do this again. So let's say you start, your examples are two-dimensional, x1, x2. All your examples look like this. But I'm going to do this feature expansion trick by adding a new feature, which is always a constant, and I'm going to put it as the first term. So that will be 1, x1, and x2. My initial weight vector is W, which is 0 according to the algorithm, right? So I start off with, and I'm going to write it as a column here because I have more space. So initially I have 0, 0, 0, and let's say I make a mistake on this example. So, and let's say this is a negative example, and it's 0. So you make a mistake, so you subtract. So you update your W as this minus some 1, x1, x2. Which means you automatically, which gives you minus 1, minus x1, which means you've automatically updated your bias feature. The weight for your bias feature. The bias feature will be 1. The bias weight is whatever it is, some B.
So because the dot product is only the test.
Yes.
Not the, well, there's a dot product there, WTX.
Yes, WTX plus B.
Oh, right. Okay, I see.
You're adding that constant term. All you need to do is somehow figure out a way of adding a constant. This is kind of a boring point, but I'll keep saying this till it sinks in, partly because it's one of those things that's so easy to forget. Okay, another let's kind of start stepping through this algorithm and looking at some details. Just to point out, if you make a mistake on a positive example, you add the features. So it's an additive update. Actually, it's an additive update in both. If it's a mistake on a positive example, you add X to W. If it's a mistake on a negative example, you take it away. And this has a very cool geometric interpretation that we'll get to in 3 minutes. R here is a constant as far as the way I've written it. It's called the learning rate. It's a small positive number, typically less than 1, and it determines how fast convergence happens. You need to pick the learning rate carefully. If you start your learning with 0, as I have described here, then actually the value of R doesn't matter. In practice, you probably will start it at some random point so that it works slightly better. So then R might matter more, and you have to pick R, and you do this by cross-validation. And question?
Can you explain why the value of R doesn't matter if we start with 0?
Right. So did I ask this in a homework question, or did I just mention this? I think I just mentioned it. Okay. So to see that, what you should do is think about, let's say you start off with 0. Every update looks like this. So you start off with W0, which is 0. Then you make a mistake. Let's say you keep making mistakes. So you start off with 0, and then you make R, Y1, X1. Then you go to R, Y1, X1 plus R, Y2, X2, and so on. Your final weight will always look like this. And if R is a positive number, the sign of this thing doesn't matter. So you say W0 is 0. An example X1, Y1 comes in. Let's say you make a mistake. You say you update your weight vector. W1 is W0 plus R, Y1, X1, which is equal to, right? Then the next example comes in, X2, Y2. Let's say you make a mistake again. So W2 is W1 plus R, Y2, X2, which is, this was W1. So it is R, Y1, X1 plus 2. So this R is always there. And because at test time you're going to make a prediction. The way you make a prediction is you take the W dot product with the new example. And the sign of the dot product does not change if R is a positive number. Only the sign. Yes.
You mentioned that if R is 0, then it's as if it doesn't matter whether it's there or not?
No, if your initial weights are 0,
okay.
If your initial weights are 0, then the value of R doesn't matter.
Okay.
If R is equal to 0, there's no learning because it remains at whatever you started off with. Yes.
So this is looking like it's R times the sum of all your mistakes.
Yeah, exactly, and that's called the dual representation of the perceptron.
And we don't have to normalize it because we only care about the sign.
Yes.
I think if R is 0, but the initialized W is not 0, it still don't learn.
If R is 0, there's no learning ever.
Yeah.
Right? Because you
Yeah,
never
so
change.
it doesn't matter if the W initialized is 0 or not.
If R should never be 0. R should be a small positive constant. Positive, not 0. Okay. The important point to notice, which is fairly obvious here, is that updates happen only on an error. If there's no mistake, the weight vector doesn't change. So this is a mistake-driven algorithm. And we'll prove in a little while, that this is a mistake-bound algorithm as well. Okay? And the final point is, right, so this is really the vanilla version of Perceptron. This is the simplest version that you'll see. There are many variants, and in practice you will end up implementing one of the variants because they are more robust. Is that a question?
Yeah. So I can't understand exactly why it's a bad thing if R is not affecting.
Oh, it's not a bad thing. It's just an observation.
Okay.
If the initial weights are 0, then R doesn't affect. You might want to start the initial weights at something else because you might know something about your data. It's not a bad thing. It's just an observation.
Okay.
And the other thing I wanted to mention is that here I've written mistakes as, let me get to red so that it's more visible. So a mistake is simply checking if yi, the true label, is not equal to y prime, the predicate label. I can rewrite this as that term at the bottom, which is simply checking if yi times the dot product is less than 0. If the dot product is positive and yi is negative, then it's a mistake. If the dot product is negative and yi is positive, then it's a mistake. So if they have different signs, then it's a mistake, which means their product is less than 0. And in practice, this version of it might be an easier thing to implement, and also gives us some generalizations, one of which you'll be implementing in your homework, called the margin perceptron. Any questions about this?
So why even bother with the R?
Why even bother with the R? Because in practice, what happens is the R is not going to be a constant. It's going to keep decreasing every time you make an update. The initial initial mistakes will be more influential. Eventually, sometimes it leads to better convergence properties. Yeah. So in practice, this property holds only when R, the one that the question was raised, that property holds only when R is a constant, so that you can multiply it away. In practice, it's not a constant. And weirdly enough, well, not weird, but interestingly enough, the perceptron update is actually stochastic gradient descent for a particular objective. We saw stochastic gradient descent for the least mean squares a few weeks ago. It turns out this is another stochastic gradient descent, and I'll mention that in a while. Okay, so let's talk about, let's spend some time trying to look at the intuition behind this update. Version of the story, and then present a version of the story. So, make a mistake on a positive example, you add x to w, a scaled version. If you make a mistake for a negative example, you subtract x from w. I've summarized that on top. And let's say we made a mistake on a positive example, which means the true label y is positive, but w dot x is negative. So what we do, what the algorithm dictates, is the new version, wt plus 1, is wt plus x. Why is that a good thing to do? To see that, we need to compare the dot product of the two dot products in question, wt dot x and wt plus 1 dot x. What changes in the dot product because of the update? And it's fairly simple. Wt plus 1 is wt plus x. So the dot product is simply the old dot product plus a term that is just x transpose x. This is x squared, which means it's positive. Which means what has happened is the new value, wt plus 1 dot x, has increased, is greater than the old value. What that means is you had a positive example and the score for it was negative. The score is the dot product. The score was negative, so you made a mistake and you made an update such that the score becomes slightly more positive. Perhaps not greater than 0, but if you keep doing this again and again, eventually it will cross the threshold of 0 and it will stop making mistakes. And that's also the intuition behind the mistake bound that we will derive. And you can make a similar sort of an argument for negative examples as well. Questions about this version of the story? Yes?
Why not simply add the magnitude of mistake directly? If we are calculating W transpose X, we know how
right. Excellent question. How far it is. Right? You know that value from 0, the difference from 0, so you can directly add some scaled version so that the eventual update crosses this threshold. That update is a variant of Perceptron called the aggressive update. And if you're feeling left out about this, grad students, you'll be implementing the aggressive update. And interestingly, what happens, the aggressive update is simply a particular choice of the learning rate. In practice, it ends up being a certain way of picking the learning rate. If you select the learning rate in a certain way, it is as if you've chosen the right one. You made the example correct.
But in this case, learning rate will change with...
You will keep changing the learning rate on a per example basis. That's good intuition. Yes. Other questions? Let's look at the geometry of this, because personally I like to think of the geometry of perceptron and linear classifiers more than the algebraic version, because it gives some intuition slightly better. Remember that we are in the land of linear classifiers, which means the separator, the classifier, is simply a line or a plane that separates the space into two parts. And the way I like to draw this is, you have a line and the direction indicates what's the positive side here. So an example that falls on this side will be labeled positive according to this plane. Example that falls on this side will be labeled as negative. So say we have a weight vector, and I'll call this W old. A new example comes in, x, and it's a positive example, x comma plus 1. And remember that x is a vector, it's a point, but every point is a vector, so I can write it as this arrow here. And according to this weight vector W, it lies on the wrong side of the hyperplane. It lies on the negative side, which means we've made a mistake. So the update rule on top dictates that you need to add x to W. So we made a mistake on a positive example, and what we do is just W new is W old plus x. The nice thing about 2 dimensions is that we can actually draw the vector addition rule. I hope you remember this from, I don't know, first grade or something, where you translate the old we need to add the black line here with the blue line, that's equivalent to this, creating this parallelogram and just looking at the one of the diagonals. And that gives us the new direction, and that's the W new. Is this geometry clear? And now what has happened, I have taken an extreme case here, an extreme example, where what has happened is the new weight vector immediately corrects the mistake. It puts the data point x on the right side of on the correct side of the hyperplane. That doesn't have to happen, but eventually it will. Let me repeat this statement, the whole thing again, for negative examples, so that if those of you who didn't catch it the first time, get it again. Say we have a weight vector W, this time it's pointing down and it will label this side of the hyperplane as positive and everything on top as negative. And a new example comes in, and it lies on the positive side of the hyperplane according to this weight vector, W old. So what we need to do is W new is W old minus x, right? Y times x is minus x, because y is minus 1. So again we apply so we need to update the weight vector, and this time minus x is the opposite direction. We complete the parallelogram, look at the new weight vector, and it changes the hyperplane. So it gives us a new hyperplane that now reduces the dot product and effectively, eventually will put the example on the negative side of the hyperplane, of the updated hyperplane. Questions about the geometry? Yes?
I have a question, but not about geometry.
Okay.
I think this method, they treat every feature like equally.
Yes.
So what if when is there some possible that in some when we add something on some W but manage something in another W? It's kind of
So let me try to paraphrase your question just to see if I understand it.
More than 3 dimensions in case we have some W, but actually some need to be added, some need to be managed to feed the data. But this way they will.
So if I understand you correctly, what you're asking is it possible to make some features more important for an example than others? Is that what you're asking?
Actually, no. I just want to say, if you want to add something to W, everything in W will be increased.
Yes.
Is there some possible that something need to increase, something need to
No. No. At least this algorithm, what it does is either you add all elements of W or subtract all elements of W. The reason being, how do you know what to increase and decrease? The only piece of information we have is the feature vector and the label. we don't know that these features are good and these features are bad. So the hope is, over the course of the data set, the weight vector W will learn this by iterating over the data multiple times. It will assign, basically think of the W as assigning a score for every feature, right? And so all you have, what you get at the end of this process is for every feature you get a particular number, right? And the hope is at the end of learning, the features that are correlated with positives will get a positive score, and the features that are correlated with negative examples will get a negative score. And that happens not at one step, but it happens in aggregate over the data.
Another question.
Okay.
So this method cannot find some features important than others.
Oh, it does. At the end, it does.
Okay.
Yes.
So right now, if you consider your previous data point again, it's going to be wrong now.
Yeah. Right. Hold on to that thought, because for that we need a theorem called the Perceptron convergence theorem, and we'll see the proof of that.
Is there any parallel version of that?
There is a parallel version which basically says, let me split the data into multiple pieces, run the perceptron algorithm on each piece separately, and then pull them all together and take the average and then iterate. It comes with some weaker guarantees. So yes.
Does this algorithm affected by the order of the data?
It's not.
It's not.
It's not. It cannot be, because we do not have any control over the order in which we have presented the examples. So it cannot be affected. It should, if it's a good learning algorithm, it should not be affected by the order. In general, if you remember the mistake bound or the online algorithms, we do not have any control over the order in which we are presented with examples. Okay, so it's easy to write an algorithm. Anyone can come up with one. The important point is we need to prove things about it. We need to say that it actually works. And before getting into the the details of the proof, a couple of points about learnability of Perceptron. First of all, you need to remember that Perceptron only learns a linear separator, which means try what you may, without any extra effort, it cannot learn a function that cannot be linearly separable. In the couple of lectures back, we looked at the class of linear classifiers, and I pointed out that there are some functions which cannot be linearly classified. The classic example there is the XOR function. And the perceptron algorithm cannot learn XOR, parity for example, or arbitrary Boolean functions. It can. There is hope for learning functions like conjunctions and disjunctions and M of n functions, functions which are linearly separable.
When you say linearly, does it, and like when you're talking, to go to like linear regression statistics, when we say linear, we mean linear in the coefficients, but there's a number of functions that could be coerced to be linear.
Yes, and that's what we will do. We will coerce the functions to be linear even for classification by blowing up the feature space. And that's why I introduced the blowing up trick before this, is to point out that even though some functions are not linearly separable, you can use that kind of a trick by basically going to polynomials, by making your basis features monomials to get effectively a polynomial. But if you just run it on the data as is, it need not work. So the point that Perceptron can only learn linearly separable functions is really important, and in fact it was pointed, the most influential source that pointed this out was this book by Minsky and Papert called Perceptrons. It talked about the geometry, and it came out in 1969, and it promptly practically killed research in this field. Because suddenly, in 1958, when the perceptron algorithm was introduced, it was presented as if now we understand how the human brain works. We know everything now. It's only a matter of time, 2 years before computers will take over our life. A decade later, Minsky and Papert published this book that said, it can't even represent XOR. So like, if it can't do XOR, then things are terrible. But the fact is, so that's just a lesson in how research progresses. But the fact is, you should remember that the perceptron algorithm absolutely cannot, by itself, learn a function that it cannot represent. And this is a lesson that's not just for perceptron, but in general, it's true for all machine learning. If you have a class of functions and that class cannot represent a concept, then no learning algorithm for that class can learn that concept. So there's no, it's not a magic bullet here. So, okay, let me just quickly summarize the algorithm and before getting on to the math. What you need to know is you need to know the perceptron algorithm. If I wake you up in the middle of the night, you should be able to tell me the perceptron update. I won't do that, but just to keep you on your toes. You should understand the geometry of the perceptron update. It's important that you understand the geometry because this geometric intuition will also help us understand other algorithms coming up, in particular support vector machines. And you need to remember that the perceptron algorithm learns linear classifiers and only linear classifiers in whatever feature space you present. Questions about the algorithm before we move on? Or any of these things? Okay, I can see you guys are reaching for the proof. So let's go on to the next part, which is the mistake bound. So if the perceptron algorithm is a mistake-driven algorithm, but to actually show that it is a mistake-bound algorithm, I need to prove that it makes only a small number of mistakes. And let's try to prove that. There are two theorems here. I'll only prove one of them. And in fact only state formally and prove one of them. This is called the perceptron convergence theorem. What it says is, if your true function is linearly separable, meaning there is some weight vector, let's call that u, if there is a weight vector u that can possibly separate the data, then the perceptron algorithm will find some weight vector that will separate the data and make only a finite number of mistakes. The other theorem in play here is called the cycling theorem. And in fact, this was introduced in that book that I mentioned, Minsky and Papert. And the cycling theorem says, if the data is not linearly separable, if it is not linearly separable, like the XOR, then it will eventually, what it will do is it will hit some weight vector and keep repeating it multiple times. So you will basically get stuck in an infinite loop. You will cycle through the same set of weight vectors again and again. Okay? So the first one is a positive result, which says if the data set is linearly separable, then the perceptron algorithm will find a linear separator. The second one is kind of a negative result, which says if your data set is not linearly separable, then it will get into an infinite loop that will cycle through the same set of weight vectors at each over the course of updates. I'll be proving the convergence theorem. I just want you to know the cycling theorem, and you should be able to prove the convergence theorem as well. Is the intuition of this thing clear? To prove it, I need to introduce a concept called the margin. Now, this is one of the most important concepts that you will learn today, because this will keep coming up again and again. And intuitively, the margin is the gap that you have between the positive and the negative examples. If that gap is too small, then your learning algorithm has very little room to play. If that gap is big, then you can easily find a weight vector because there's a lot of space. So let's make this slightly more formal. Suppose you have some points, positive and negative points like here, and you have a hyperplane, this line here. Then the margin of this hyperplane, the margin of just this hyperplane, is the distance of the closest data point to that hyperplane. So in this case, the margin of this hyperplane is this distance here. Okay? But this is just for the hyperplane, it's not a property of the data. The margin of the data is search over all hyperplanes and find the one that maximizes this distance. So try to find a hyperplane such that it is farthest from both positive and negative points, equally far actually, and that distance between these points or the negative points and the hyperplane is called the margin of the data set. Questions about the margin? Mathematically, but you should be able to see how you can basically write down an equation that all you need is just search over all data points, find the closest one, and search over all hyperplanes, find the one that maximizes that term. Questions about this? Yes?
So if there's a lot of noise, then that can wipe out the separability.
Absolutely. And in fact, in defining this, I'm assuming that the data is separable. Right? Yes?
So the margin have to be only one in the data, right?
The number one?
Margin. There only one margin in the...
For a data set, there's only one margin because there's only one maximum. Yes. Questions? We're using this concept of a margin multiple times, and in fact, I'm fairly certain the same slide will show up again maybe in a month or so. And it's important that you get this at an intuitive level rather than in addition to maybe the formal mathematical definition. Questions? Yes?
How do we know the maximum exists?
How do we know the maximum exists?
Just like, we have like a sequence of hyperplanes that, there's...
So you have a finite set of points. So you only have a finite set of points. So there must be 2 points of opposite labels. So if it is separable, there must be 2 points of opposite labels that are closer. Right? And basically the distance between them, that distance between them, divide that by 2, that's the margin. So it exists because you only have a finite training sample.
This is the opposite of finding the minimum cost of all the error between the line and the data. It's the same as it's the opposite of the first concept we learned of finding the minimum, assigning a cost to each label, and then finding the minimum in the data set.
It's actually quite related. In fact, the way you should think about this is there are some points, in this case, there will be some points that lie on the margin. So in this case, this point lies on the margin, and these 3 points lie on the margin. And these are the points where you are first probably likely to make a mistake. Because if you move this thing around, if you turn the weight vector instead of this, if you have something like this, there's an increased possibility that you will make a mistake on the ones that are on the margin, a plus here and a minus here. Chances are you're not going to make mistakes on those. So with this kind of a gut feeling understanding of margin, I can now state the perceptron mistake bound. The mistake bound was simultaneously discovered by Novikov and Bloch in 1962. So some people call it the Novikov Theorem, some people call it the Bloch-Novikov Theorem. And it goes this way. Say you have a finite set of training examples, x1, y1, x2, y2, till xm, yn. So you have m examples. And for the example consists of a feature vector and a label. The feature vector is this vector x, xi, which is n-dimensional, so the dimensionality of the space is n. And the label is -1 or +1. And I'm also demanding that there is some number r such that if you draw this giant ball, all the points are contained inside it, and the radius of the ball is r. That's basically the statement here. Every point is contained inside a ball of size r. Suppose this data is separable. If the data is separable, then there exists some weight vector u. We don't know it, but there is this true weight vector u which perfectly separates the data. Not only does it perfectly separate the data, there is a margin, right? Because there must be some points which are close, and because we only have a finite number of points, it assigns the correct label and is the closest point will have a label, will get an activation score of gamma. So, in order to correctly separate the data, all you need is y times u transpose x is positive, right? Y and u transpose x have the same sign. Let's say the closest one is gamma, and then gamma is the margin. Is that clear? Is the setting clear? We'll stare at this a little longer. Let me just complete the theorem. If these two conditions hold, namely all your points lie inside this ball of size r and the margin of the data set is gamma, then the perceptron algorithm will make at most r square over gamma square mistakes. And this is the statement, the entire statement of the perceptron mistake bound theorem. So let me just clarify a few points and then you guys can ask questions. The first thing is this condition that the point should lie inside a ball of size r is nothing special. Because given any finite set of points, I can always find a large enough circle that contains all of them. Right? So let's call the distance of the farthest point from the origin, let's just call it r. And that satisfies this first condition. So the first condition is trivial. It's always possible to find an r. The second one is the more subtle point here. The data is, this assumes that the data is separable. So let me first try to hide this so that so the middle block here simply says that the data is separable with a margin gamma. Now, this is actually a very strong condition. We are assuming that the true data set, the data set that we have is linearly classifiable, meaning the true concept is a linear classifier. Remember that this doesn't have to be the case. For certain kinds of functions, it will not be the case like XOR, or in the worst case, you could also have noise in the data that renders data sets linearly non-separable. So it's a very strong condition, but this is the condition in which we are able to prove the theorem at this point. And the margin gamma is a complexity parameter. It tells us how easy or hard is this data set from a learning perspective. Because if the margin is really small, then we have very little wiggle room. If the margin is really large, pretty much any weight vector will classify it. So if the margin is small, you expect learning to be easy. If the margin is large, you expect learning to be hard. And in fact, that's exactly what the mistake bound does for us. Because notice that the mistake bound here is r square over gamma square. So if gamma is small, the number of mistakes you make is really large. If gamma is large, then you will make fewer mistakes. So the margin is the complexity parameter. And another kind of a side point that I encourage you to explore on your own time is we've assumed that this true concept, the true weight vector u, is a unit vector, and that's really not needed. If that assumption was not there, you could always normalize it, and when we go through the proof, it won't make too much of a difference. You can keep normalizing it and it will change the mistake bound a bit. but it will give us another mistake bound, which is okay. So the right way to read this theorem is, we have a binary classification problem with n-dimensional inputs. If the data set is linearly separable, then the perceptron algorithm will find a linear separator, only making a finite number of mistakes. Is the statement of the theorem clear? Questions about any of the math or the intuition? Yes?
Can you explain why having a smaller margin will lead to more mistakes?
Think about it this way. A small margin means there is, intuitively the margin is like a distance between the, first of all, the data set is linearly separable, meaning there is this cloud of positive points, there is a cloud of negatives. The margin is the distance between them, the shortest distance between them. If that margin is really small, these two clouds are very close to each other, which means there's very little room to randomly find
A correct weight vector, correct vector.
exactly. If you have a lot of room, you might be able to. So let me give you an example. Let me try to make this. Let's say if you can do a proof by pictures. Let me go to a slide where there's more room. So let's say we have positive points. Say we have some positive examples here, and let's say we have some negative examples here, far away. This is a weight vector that correctly classifies it, but then so is, and with the positive being this way, but then so is this one, right? And in fact, so is, well, almost that one. Make it better. So is this one, and this one. So there's a lot of room. There are many possible functions that can correctly classify. On the other hand, say your positives and negatives were very close by. So you have plus, and say your negatives. It is linearly separable, right? The pluses and the minus, there is a line that separates them, and in fact it's probably this line. But I can't, the number of lines that so I want you to take the following statement with a pinch of salt, because we're not counting the number of lines. But the possibility of making mistakes is much higher, right? In both cases you have an infinite number of lines, but we're not counting lines. Because there's more room, and we have, assuming that we have normalized the true weight vector to unit vector, we don't have too much wiggle room in this gap here. So you can do this, but this is all the space that you have. So intuitively, smaller margins imply easier learnability. And in fact, this same intuition also shows up for support vector machines. Does that clarify the question?
You said easier learnability, but you'll make more mistakes. Is that?
No. If I said that, I take that back. What I mean is, you'll make fewer mistakes, and hence it's easier. Fewer.
Okay.
Yes.
So if the margin is larger, you make fewer mistakes, and it's easier.
In fact, if the margin is larger, you make fewer mistakes, hence it's easier.
Okay.
Can I have a question?
Sure.
Why gamma is margin? Why is margin?
What do you mean?
You mean the data has a margin gamma?
So I've called the margin gamma here.
Yeah, why gamma is a
Oh, good. So the reason for that is because u is a unit vector. So to see that, let's try to find the distance of this point from the hyperplane. Okay? So this point here, let's call this x, and let's call this u. The distance of the point is, how do you calculate the distance of a point from a line?
Substitute that point in the equation of that.
Right. So if this is u, writing now. Let's try again. Let's call this point x, and this is the line u dot x equals 0. And the distance of the line from this point is u dot x absolute value divided by the norm of u. What we want by definition, the definition of the margin is the shortest such distance. For this particular hyperplane, it's the shortest distance. So you try out all possible data points and you find min over x. But instead of stating absolute value, I could just as well have replaced it with y times u dot x. Because if it's a positive example, u dot x is positive. Y is positive, so it's the absolute value. If it's a negative example, u dot x is negative, y is negative, so that gives us the absolute value. In both cases, this is equivalent to this. So you get y dot x divided by norm of u. And minimize. Okay? The data set is linearly separable, which means this minimum is positive. The minimum value of this is greater than 0. But what that means is for all x, y, it's yi u transpose x is greater than, trivially, the minimum I'm going to call this guy the margin. Okay? I'm going to call that gamma because that is the definition of margin. And typically, you'll see the symbol gamma being used for margins. Okay, so now that we have only 20 minutes left, I think that should give us enough time to go over the proof. So, theorem simply says, if the data set is linearly separable, then the perceptron algorithm will find a linear separator. To prove this, we need to make a few assumptions. We are going to work in a setting where the initial weight vector is 0. Let's also assume that the initial learning rate is r. We've spoken about it, so I'm not going to talk about it too much. All the examples are contained in a ball of size r, which means, what that simply means is that for all xi is less than or equal to r, or the norm of xi is less than or equal to r. And we just spoke about the margin. For every data point, there is some true weight vector u such that y times u transpose x is greater than gamma. So the only two things that we have which is independent of this particular data set are gamma and r. So this proof proceeds in 3 steps. First, I'm going to show you that after making t mistakes, the dot product of the true weight vector u and the tth weight vector w is greater than some t times gamma, is t times the true margin. It's a fairly simple process, so let's go through this. So notice that after an update, your weight vector w, wt plus 1 is simply wt plus yx, which means u times wt plus 1 is simply u times is equal to u transpose wt plus yx. But by definition, we know that yi times u transpose x is greater than the margin. That's how we've defined the margin, and it doesn't matter which xi, yi we pick. Yi times u transpose xi is greater than gamma, and that is just the assumption in the theorem. So we have this fantastic recursion now. Note, this is greater than u transpose. So u transpose wt plus 1 is greater than u transpose wt plus gamma, which is greater than u transpose wt minus 1 plus 2 gamma, and so on. But we know that w0 equals 0. So just unrolling this recursion just gives us this statement that we wanted to put. Okay? Is that clear?
So are you getting further away from the margin as you get more, as you make more mistakes?
Hold on. I don't want to commit to that statement yet.
Okay.
This is just one statement. On the other hand, we have another bound, which is after t updates, the norm of the weight vector, the norm square, is bounded on top by t times r square. And again, the way to prove that is also fairly simple. The norm square, you just unroll the update. Wt plus 1 is simply Wt plus Yx. And this is just a square. So this is just a quadratic form. You expand the quadratic form. So this is, it can be, I'm going to do it a little bit messily right now. This is Wt plus Yi xi transpose Wt plus x. The norm square is simply, so for any vector z square is z transpose z. That's what we've done here. But this is equal to this quadratic form because you just expand the quadratic here. So you get w square plus x square plus 2 yi w transpose x. Is that so far so good? Or bad? Okay. So now let's start staring at these terms. The first term is just Wt square. There's nothing we can say about it. The second term here, for this particular example, think about why we updated Wt. Because we made a mistake. We made a mistake means y times w transpose x is negative. So because we made a mistake, we updated it, which means the second term is definitely negative. Otherwise, we wouldn't have made a mistake. And we wouldn't have made the update. So we know that this term is negative. And we also know that this term, by assumption, is less than r square. Because we know that every data point is inside this ball of size r. Putting these two things together, what that means is this is negative, so if we get rid of this, we get an inequality here. And we bound this guy on top, this becomes r square. Again, we have a recursive, again we have this which is just a function of t, and we know that w0, the norm of that equals 0, because we initialize it with a 0 vector, and we keep doing this again and again. So Wt plus 1 square is less than Wt square plus r square, which is less than Wt minus 1 square plus 2r square, and so on. So Wt plus 1 square is less than t plus 1 times r square. So you get this statement here. Questions? Either this is really simple or this is completely gone on top. If it's really simple, tell me. If it's gone on top, tell me. Either way, there's only one answer. Yes?
I'll be honest, it's gone over the top of my head.
Excellent. Thank you.
I'll be the vulture.
Which one do you want? What do you want me to repeat?
What was the question again?
What would you like me to repeat?
Can you repeat going over how, well, I'm just trying to see in that substitute, we just said after that many mistakes, you have the t times r square. I'm just wondering where did that t come from?
Excellent. So let's go back to the previous one now. And thank you for asking the question. So let's go back to instead of it's the same logic as we had in the first step. So do you see this point here, this inequality? this is greater than this. Why? Because this guy is less than gamma. Right? So what we know is
If we put that in as gamma, then that one, that other side is naturally going to be greater.
So you know that U transpose is greater than U transpose WT plus gamma. We know this. But we also know that U transpose WT is greater than just it's true for all T, right? So we know that it's greater than U transpose WT minus 1 plus gamma. And so on. We know that U transpose W1 is greater than U transpose W0 plus gamma. But we know that W0 equals 0.
So that goes away.
So that goes away.
Yeah.
And we add all these things up. And everything gets cancelled. You're left with U transpose WT, and all these, there are T plus 1 gammas here.
Oh, okay. Thank you.
So you get U transpose WT plus 1. True for all T, so that proves the result. The same argument in this case. We know, so do you want me to repeat this for the R square case? We know that WT plus 1 square is less than this thing. And this is true for all T. You keep substituting the same thing again and again, all the WTs get cancelled.
And that leaves us with R2s, and we just sum up R2s. And that's it.
Exactly. Exactly.
Thank you.
Excellent.
So number 1 gives us a lower bound of the size of the weight vector.
Yes.
And then number 2 gives us an upper bound.
Yes, and all we need is just to line them up together, which is what step 3 of the proof is. So just to summarize, number 1 told us that after T mistakes, U transpose WT plus 1 or U transpose WT is greater than T gamma. Step 2 of the proof tells us that after the same number of T mistakes, the norm of the weight vector is less than T times, or the norm square is less than T times R square. So let's start piling them together. First, let's write down the second thing. I've just taken the square root everywhere. So R times square root of T is greater than the norm of the weight vector. No surprises here. This is the same as this. But here comes a slightly more devious step, which is saying that the norm of a weight vector, we know that U is a unit vector. This is part of the assumption. This is where we are going to use the fact that U is a unit vector. The norm of the weight vector can be used to define the dot product of U and W. Why? Because in general, if you have two vectors A and B, A dot B can be defined as the norm of A times the norm of B times the. So you have a vector A and a vector B, and this is the angle between them. Right? We know that in this case, U transpose W is exactly that. But we know that norm of U is 1. We know that the cosine of the angle is less than 1 by definition, which tells us that U transpose W is less than the norm of W, less than or equal to. Is that okay? If you don't like this derivation of this, another way of thinking about the same thing is you can just appeal to this inequality called the Cauchy-Schwarz inequality. It's the same thing. If you feel that it's better to write it away as a named inequality. But is this statement clear? So now what we have is we had this norm of the weight vector at the tth step, and we know by Cauchy-Schwarz that it's greater than or equal to U transpose WT by this step. But now we have we are in this joyous position because we have this U transpose WT and we know something about it. So let's bring that up. U transpose WT is greater than T gamma. That was step 1 in the proof. Right? Okay? Basically the proof is over now. We've now connected, we've got an inequality on both sides. It's independent of W, it's independent of U. It only involves T, R and gamma. Let's just pile them together and pull the T's out and onto one side and R and gamma to the other side. We get T less than or equal to R square over gamma square. What is T here? T is the index over the number of updates. It keeps increasing. On the left hand side you have a quantity that keeps increasing. On the right hand side you have a quantity that's a constant, R square over gamma square. Which means the number of mistakes can never be more than R square over gamma square. I'll give you some time to stare at this and convince yourself that I'm not lying. I saw you first.
Does this mean that the learning rate has no effect on whether or not it's going to converge? Like, what if the margin was like 0.1 and the learning rate was 2?
The learning rate ends up being a term in the denominator of this thing. So small learning rates, slow convergence, large learning rates, large convergence.
But if there's a small margin, like it's linear is separately separable. By a small margin, if you have a fast learning rate, will it still converge?
It basically competes. It competes with the margin. So if you have the learning rate, you get a term that looks like this: R square over little R square gamma square. Or I don't remember if there's a square, but it doesn't matter because you can always use the learning rate as a square. So what this means is small margin, large learning rate. This whole thing can be large or small. It really competes. And in fact, it's a minor tweak to the proof. So you should be able to derive this. If you just follow through the same steps, but introduce the learning rate. In fact, it might even be an exercise that I would recommend. I saw another hand come on. Yes?
So could we do better than this if we update on the non-mistakes too?
Good point. In fact, if we update on non-mistakes, what we get is better generalization bounds, but not number of mistakes. Not necessarily number of mistakes. You get better guarantee of future performance. That's all you get.
So assume there's no noise in data, right?
It's not exactly the same. I'm assuming that the data is linearly separable, even with the noise.
T is an index, right?
T is an index.
So that's the how many examples you need.
Mistakes. How many mistakes?
How
T
many
is,
mistakes
yes.
you need to achieve is your target, right?
No, T is a counter that keeps increasing every time you make a mistake.
You're only updating W at mistakes.
You're only updating W at mistakes.
Yes. So WT plus 1 is after making T plus 1 mistakes.
Yes.
So then you are saying the number of mistakes that you could do
Yes.
should be less than
This constant.
this constant.
Yes.
If not, it is not separable.
It's the other way around. If it is separable, the number of mistakes will be bounded by this constant. And yeah, sure. What you just said is the contrapositive.
I was thinking about if the R is a little big and the margin is very small, can that end up into infinite?
If the margin is 0, then you go to infinity, which basically says that data is not linearly separable. If R is infinite, you will end up at infinity. That says that your data points are basically at infinity. So, I want you to go back and savor this result a bit, but let me give you a few points. Yes?
Talking about putting the learning rate in the denominator, to me that's really disturbing because then you would want to pick an infinite learning rate. because then you would have t would be less than or equal to something that's very close to 0.
That's an excellent point. I've never thought of it. So, if your learning rate keeps getting bigger, you will have to think about this. Find me after class. Actually, that's pretty cool. There's probably a very simple answer, and we'll talk about this. Yes. So, let me tell you what the summary of this statement is. You're getting a bound on the number of mistakes. So, let's go back to just a statement of the theorem. You don't have to, you probably know this by now. What we are saying is, if the data set is linearly separable by some unit vector, then the number of mistakes, here's the coolest part of this, the number of mistakes is independent of the size of the data set. The mistake bound does not care about how many examples you have, which is pretty neat. It doesn't matter if you have a million examples. If your data set is easy, you'll only make a very small number of mistakes. Now that's the biggest, for me at least, that's the most counterintuitive statement here. It doesn't matter. It's not even going to use it because it's going to stop making mistakes way before you get to the end of it. And that's the point that I want you to think about. And a couple of other points, just a reminder, the number of mistakes is less than r square over gamma square. You should be able to, you should know this mistake bound, and many other algorithms have a similar sort of a behavior where the bounds are characterized by the margin in the denominator and something that looks like capital R in the numerator. R is upper bounded by some function of the dimensionality. And what I want you, as an exercise, I want you to prove to yourself, it's not a very difficult proof, I want to prove to yourself that if you have only Boolean functions like we had before, like conjunctions and disjunctions, then R square equals n, the number of bits that you have. Okay? Gamma, on the other hand, is not a function of the dimensionality, it's a property of the data. Gamma defines how difficult this problem is. So there is one aspect to this mistake bound, there's a property of the space that your examples lie in. There's another aspect to this mistake bound, there's a property of your data that your examples lie in, that represent your true concept. So a few examples that you should try out. Say you have disjunctions. Try to instantiate these values of R and gamma. And just to make it very simple, pick two-dimensional data points. Consider the disjunction x1 or x2, and on paper try to compute the value of gamma for that data set and try to generalize that to arbitrary dimensionality. Try to think about how many mistakes that this algorithm will make on k disjunctions. And the final thing I want to leave you with, actually not the final thing, the penultimate thing I want to leave you with is, this is a tight bound. Meaning you can, for certain concepts, find a sequence of examples that forces the algorithms to make these many mistakes. And try to find a sequence of such mistakes for k disjunctions. Okay, news. There's no assumption about the distribution of the data. The algorithm doesn't care what your data looks like. If the data set is separable, then it will find a separator, even if the source that's giving you the examples is acting adversarially. The bad news is most functions that we care about are not linearly separable, either because they are not linearly separable, like the XOR, or because there's noise in the data. Which means there is no realistic hope that we'll never make mistakes again. But even then, there are robust variations. In particular, we'll start the next lecture with something called the average perceptron, which tends to have very good behavior. And in fact, that will be the version of perceptron that you should implement, once the semester is over, unless I ask you to do it in the homework. So what you need to know from this section is you need to understand the mistake bound. You need to know what it looks like, what it means, and you should be able to prove it. So please go over the proof and come back with questions. And I think I'm a minute over time, so I have office hours And please don't forget your project proposals.